Welcome back. Hope you're doing well. So, we are in the third week of our data analytics lesson. So, so far we identified what is data analytics and how data plays a critical role in decision making. So, let's start today's lesson there. So we defined data analytics as the process of inspecting, cleaning, transforming, and modeling data to discover useful information and draw conclusions and support decision making. So we discussed that we have produced more data in last 2 years than all human history combined. So the future belongs to those who can analyze this data intelligently. So that's why we call data analytics is the heart of modern IT industry. Right. So you can remember in our first week where we discussed about data lifecycle. So it is an iterative process with 6 phases. So it's a process that guides us how we handle data, right? So from the moment we identify a problem to collecting and analyzing the data to finally making a decision. So throughout that data life cycle is the process of how we handle data. So it is an iterative process with 6 steps, right? Steps are discovery, data preparation, model planning, model building, communication results, and operationalize, right? So it is an iterative process. So what do we mean by an iterative process? So iterative means the process is not linear, right? So we are not just going from step 1 to 6 linearly. Instead, we go back and repeat steps to improve results or correct issues. So as an example, so after building a model, so we might realize we need more clean data, right? Or we need to clean data more. So we return to the data preparation phase, right? So after we building the model, we might realize, okay, we need more cleaner data. So we can go back, right? We can go back. So it is not a strictly linear process, rather an iterative process, right? When we communicate the results with stakeholders, right? When we communicate the result with stakeholders, they might ask new questions or give us new suggestions. So we have to go back to the discovery phase there to add that new improvements, right? So likewise, this is not an structured or linear process, rather an iterative process that guides us transform data into meaningful insights. Data lifecycle has 6 stages. Discovery. So discovery means it's the step where we focus on understanding the business problem and defining objectives. So it is the step where we try to understand the customer need or the business problem and what is our objective, right? What we are going to solve, right? So that is discovery stage. Then we have data preparation. Then second phase is data preparation. It's the phase where for that objective, the relevant data is collected, right? Then that collected data, we need to clean them and uh, organize them to ensure data quality, right? So in this phase, we collect relevant data, clean them and organize them in a manner so we can ensure data quality, right? Then we can go to the model planning. So in model planning, we follow appropriate statistical techniques and tools to build the data model, right? Uh, right. Then we have uh, model building, right? So these method in this phase, we apply statistical techniques, build hypotheses, and we build the predictive models, right? After that, we will get the results. So in the communication uh, results phase, we summarize and present insights to the stakeholders using data visualization tools, right? Or BI likewise. Then reports like Preprocessing reports likewise. Then we have the operationalization phase. So in this phase, uh, the findings are integrated into business process or the system, right? So that's in this phase we apply those findings to our uh, to solve our business problem. So this is the phase where we apply our findings. The six phases are discovery, data preparation, model planning, model building, communication results, and operationalize. Right? Then we discussed that there are three types of data analytics: descriptive analytics, predictive analytics, and prescriptive analytics. Descriptive analytics is in descriptive analytics we focus on summarizing past data to understand what has happened. In descriptive analytics, we summarize past data to understand what has happened, right? So it look at past performance and understand the performance uh, by mining historical data to understand the cause of success or failures in the past. So we evaluate the past data to understand what was happened, right? That's descriptive analytics. So all management reporting, such as sales, marketing, operations, finance, so these use descriptive analytics. And dashboards. Using dashboards, we can represent descriptive analytics results. And for descriptive analytics, we use descriptive statistics, right? For doing descriptive analytics, we use descriptive statistics, right? So as you can remember, last week we discussed about basics of statistics, right? So which is a crucial skill for a data analyst. We learned that uh, statistics can be broadly divided into two main categories: descriptive statistics and inferential statistics. Okay? Descriptive statistics helps us to summarize or interpret data. descriptive statistics helps us to summarize and interpret data. Inferential statistics helps us to make predictions, predictions. So basically, we make predictions about the population using a sample, right? Right. So then descriptive statistics can further be divided into two key types as measures of central tendency and measures of variability, right? Basically, using descriptive statistics, we were trying to find the middle value in a data set, right? Using descriptive statistics, we try to basically identify the middle value of the data set using measures of central tendency. And using measures of variability, we identified how much our data set variate from that particular middle value. So what is the dispersion of the data set? Due to statistics, we try to find the middle or the typical value in the typical value in the data set, right? You can remember there were three measures of central tendency: mean, median, and mode. So mean is basically the mathematical average. Then median is the middle value when we sort our numbers, we sort the data set in a ascending or descending order, right? Then mode is the most frequently occurring number, right? Most frequently occurring data point. So these three gave us a quick snapshot of where the most data points are centered. So think why finding this middle point is important. So why finding this middle point is important? Because finding this middle point help us to simplify the data set, right? So we can simplify the data set into a single understandable number that represents the entire data set, right? So finding the middle point helps us to simplify data into a single understandable number that represent the entire data set. Simplified data set into a single understandable number that represent entire data set, right? So let's see what that means, right? So as an example, imagine a company wants to find out that are we paying our employees a competitive salary compared to the other companies, what if they, okay, so they know how many employees are there and their salary. So they calculate the mean salary, right? The mean salary, sigma x, 9 x bar, right? So, uh, so they calculate the mean and calculate, they compare it with the average of the uh, uh, average with, they compare it with the average of the industry, no, right? So let's for an example think the mean salary, let's say it's 75,000, then uh, they see that the industry average is 70,000, right? So uh, they come to a conclusion that our mean is higher than the industry, so we might need, we might not need to increase salaries of the employees, right? So is that decision correct? Is that decision correct? Not, not exactly, right? Because the mean alone tell the full story about the data set, right? Mean alone does not tell the full story, right? That means, right? Uh, so let's think our salary data distribution is not a normal distribution, it's a skewed distribution, right? Skewed distribution, right? That means there are employees who are getting uh, very high salaries, and there are employees who are getting very low salaries, right? But combiningly, our average, let's say it's 75,000, but it's because in our company there are many employees, there are small number of employees who are getting very uh, very large salary, right? But overall, the majority of the employees are getting a low salary. So in that case, our data distribution is not a normal distribution, right? Our data distribution is not a normal distribution. So, comparing mean is does not represent actual uh, the actual picture. So in a normal distribution, the data is balanced. The data is balanced. Right? Most of employees are around the most of the employees are around earn around the earn around the same amount, right? And there is a very few employees uh, who are on the uh, very few employees who are in the extremes, right? Very few employees who are getting the higher salary, and there's very few employees who are getting the very low salary, right? So the data is normally distributed. So most of the employees are earn around the same amount, and you can see mean, median, and mode are equal, and they are in the center. Mean, median, and mode are mode. All three are in the center, right? So in this case, comparing the company average with the industry average is correct. So because in this distribution, the average truly represent the uh, typical salary. Average truly represent the average truly represent the uh, typical salary, right? So in this case, comparing it with the industry average is correct. So we you so uh, if the data is normally distributed, average truly represent the typical value. So therefore, uh, we can compare it with the let's say industry average, right? But so there, our data can be positively skewed or negatively skewed. So we might not have a normal distributed data. We might have a positively or right skewed data or negatively or left skewed data. So, so how can our data get positively skewed? Because there is a small number of employees, so let's say executives, earn significantly higher salaries. There are some executives, there are some executives who earn very high salaries. So they, even though many of our employees are getting low salary, because of this, our mean pulls upward. Our mean getting pulled upwards. Even though many of the employees are getting a low salary, because there is a small number of executives who are getting extremely high salaries, because of that, our mean gets pulled upwards, right? So mean is larger than the median and the mode, right? So in this case, most of our employees may get uh, a salary like 50,000, right? Significantly lower than the industry. Uh, but the median or the mean will say it's around 90,000 because there are executives who are getting extremely high salaries. Uh, so if the company only look at the mean, what will happen? They will overestimate what majority actually earn. So looking at the mean, they see, oh, it's our mean is 90,000. But they don't see the actual picture, which is the many of the employees are getting a salary around 50,000, right? So in this case, mean is not uh, the accurate value to compare with the industry average, right? So in this case, median is a better indicator, right? In this case, median is a better indicator. So like that, our data can be negatively skewed also. So our data can be negatively skewed or also, or we call that left skewed distribution. So there is a very few employees, let's say interns or part-time workers. So they earn very low salaries. They earn, let's say we have interns. Interns in the company. So they earn very low salaries. We have with few employees who are earning very low salary, but our most of our employees are getting a good salary. Right? Most of our employees are getting a good salary, but because of this, because small number of employees are getting a very low salary, our mean gets dragged down. Mean gets dragged down, right? So because of that, mean is less than the median, mean is less than the mode, right? So, so now if we look at the mean, we can see the company might think our salaries are too low. Our salaries, we are paying our employees a very low salary. But in reality, most of the employees are getting a good salary, right? Uh, most of the employees are getting a good salary. So in this case also, mean is not the indicator, right? In this case also, median is all median uh, can be more reliable for representing the typical employee's salary. So you can see, so you can see this descriptive statistics helps us to better understand the patterns, trends, and distributions within the data set. So, within the data set by summarizing and organizing the data. So, so that's why it's important to have that understanding about the center point, right? So we had three measures of central tendency: mean, median, and mode. So weighted mean. The weighted mean is a type of average where each data point contributes differently to the final results depending on its assigned weight. So you saw in real world data, not all values are equally important. So therefore, we assign some weight, thereby we calculate the we assigned a weight based on their importance. Then the final result will be depending on the assigned weight. So in our salary example, uh, let's say in our company we had uh, 10 we had 10 interns 10 interns uh, let's say their salary is 20,000. Then 50 junior staff, let's say their salary is 60,000. Then mid-level the mid-level staff, let's say we have 30 mid-level staff. let's say their salary is 80,000. Then we have 10 senior staff. Let's say their salary is 150,000. Right? So our what is our average will be? You can see there is a small amount of people, executives who are earning a significantly higher salary, right? So what will be our average? X bar equals sigma x divided by A, right? So our average salary will be 20,000 plus 60,000 plus 80,000 plus 150,000. So divide by uh, 4, right? So that will be around 70 77,500. 77,500. So you can see this does not represent the actual typical value. So we will calculate the weighted mean by assigning some weights. Weighted mean. So we have 10 interns with 20,000 salary. Then we have 50 junior staff with 60,000 salary. Then we have 30 mid-level staff with 80,000 salary. Plus we have 10 senior staff with 150,000 salary. So we will divide it by W sigma WI 10 plus 50 plus 30 plus 10. Right? So this will be around 71,000. Right? You can see this is 71,000. So this is lower than the mean. Weighted mean is lower than the mean. So that will be a good representation of the actual actual value that the most of the employees are getting paid. So in then we had the measures of variability or the measures of dispersion. So using these measures of dispersion, we check what is the dispersion of the data set. So how much the data points are getting deviated from the center point. The data points are differ from each other and from the how much data points are differ from each other and from the central value. So it shows us how consistent or inconsistent the data are. There were 3 measures of dispersion, range, variance, and standard deviation, right? Okay. So that's descriptive statistics. So then we will discuss about predictive and prescriptive analytics. So predictive analytics. So what do you mean by predictive analytics? Predictive. We are trying to, as name suggests, we are trying to predict something, right? So we are trying to forecast future potential or the potential future outcomes. Using predictive analytics, we try to forecast potential future outcomes. Analytics use data to determine the possible outcome or of an event or a likelihood of a situation occurring. So predictive analytics use a variety of techniques such as uh, modeling, machine learning, data mining, uh, uh, to make predictions about the future event. So here we are using uh, techniques such as linear regression, uh, time series analysis, time series is time series and forecasting, then data mining. So we use techniques like this to do predictive analytics, right? Then we have prescriptive analytics. Prescriptive analytics, right? So prescriptive analytics goes beyond predicting. So right, it's goes beyond predicting, right? It's right. It goes beyond predicting future outcomes. Also, it suggests actions, right? It suggests actions or recommendations for you can take to influence future outcomes, right? So give recommendations for next steps. It's prescribing, right? Prescribing what you should do to achieve that or to avoid that situation. So prescriptive analysis suggests actions you can take to influence future outcomes by combining data, models, and optimizing techniques. So this prescriptive analytics does not only anticipate what will happen and uh, when will it happen, but also it identify why it will happen and suggest decisions or the suggest options where you can take advantage of the future opportunity or mitigate future risks. So then in our data analytics life cycle, the second step was data preparation. Can you remember? Data preparation. So in this phase, right? In this phase is where we collect the relevant data. So this is the phase where we collect the relevant data and clean them and organize them to ensure the data quality and consistency. So this is the phase where the relevant data is collected. Data is collected collect, clean, and organize to ensure the quality, ensure data quality and consistency. So this is the phase where we do data collection, then cleaning, organizing to ensure the quality and the consistency of the data. So the quality and the consistency need to do the future analysis, right? Okay. So we will focus on this data collection first. We will focus on this data collection first. What do we mean by data collection? What do we mean by data collection? Data collection means gathering data. Data collection means gathering data, right? Data analysts collect data from various resources, right? Is collect data from various resources, such as doing a survey, databases, web sources. We collect data from various sources that we call as data collection, right? So let's understand this deeply, right? So last week we discussed, so uh, data analysts often collect data from a sample. So last week we discussed that data analysts often collect data from a sample rather than the entire population, right? We collect data from a sample rather than the entire population. Why? Because collecting data from the entire population is either impractical or either time consuming or either, right? So collecting data from a population is either impractical or either time consuming or either costly, right? Right? So therefore, uh, because of that, often data we collect data from a sample, so here why I'm saying often we collect data from a sample. So because it is not, so it is not always necessary to use a sample, right? Sometimes data from the entire population is available or accessible, uh, such as so let's say a company is analyzing salaries of its employees. The company is analyzing salaries of its employees, right? So the entire data set is available. So in that case, we don't need to uh, use a sampling techniques, right? Or let's say a school is analyzing grades of uh, all students in the class, right? So in that case, the data is available, right? So that's why we say often we collect data from a sample, right? Right. So, but in real world scenarios, collecting data from everyone in the population is either too expensive or time consuming or costly. So therefore, often we use a sample which is smaller, manageable, and representative subset of a population. A sample is a manageable, smaller representation of the entire population. So, as an example, if you can think about let's say a company like Amazon, right? So let's say Amazon wants to evaluate customer satisfaction of their products. Amazon want to analyze customer satisfactions of their products for the past month, right? So let's think for the past month, they had 10 million customers, 10 million customers who purchased orders. So it is impractical to contact all 10 million customers for feedbacks. Obvious, right? It's impractical to contact all 10 million customers for feedbacks. So instead, what they will do is they will select a random sample, let's say for 10,000. Let's say for 10,000, they collect a random sample of 10,000 customers. Then they will send a survey to those selected customers to rate their experience. So then the company analyze that responses, the responses given by the selected sample, and to estimate the overall customer satisfaction for the entire population. So this will save time, money, and resources. And still, if you apply proper statistical techniques, still it will give accurate insights, right? So this is where the sampling techniques comes. So you understood that to get a proper accurate results, right? To get accurate results, the sample need to sufficiently or accurately represent the population. So the sample need to accurately represent the population. So this is where the sampling techniques comes, right? So sampling techniques helps us to select a representative subset. Sample techniques helps us to select a representative subset of the population, so which will ensure the result of the analysis are valid, reliable, and generalizable. If the sample is an actual representation of the population, we can ensure the results are valid, reliable, and generalizable, right? So we have sampling techniques like simple random sampling, systematic sampling, stratified sampling, clustered sampling, right? So let's see what each of these are. Right. So first thing is simple random sampling. Simple random sampling. Right? In simple random sampling, we randomly pick elements from the population. We randomly pick elements from the population. Right. Think of it as we put everything into a ball and pick elements. Right. randomly pick element. So every individual, so every element in the population has an equal chance of getting selected, right? Every element or the individual in the population has an equal chance of being selected, right? So this technique is used when the population is homogeneous and uh, the complete list of the population is available. So homogeneous means the individuals in the population are similar. So example, so if you are serving a factory workers, let's say you are surveying a factory workers about their environment, right? So most likely their experience are similar, right? So that kind of population we call as homogeneous, right? Then we have stratified sampling. So stratified sampling means so the the population is divided into subgroups. The population is divided into subgroups. The population is divided into subgroups based on their characteristics. Divide into subgroups based on uh, a based on a characteristic based on a characteristic, right? Then we use random sampling to take uh, uh, take elements from each group, right? So first we divide the population into subgroups based on a characteristic. Let's say like age, gender, income, likewise. So then we use a random sampling to take elements from each group of the each group of the population, right? Right. So as an example, let's say we have uh, students, uh, 10,000 students. Let's say 60% of uh, them are male and 40% of them are male. So uh, so based on that, you select 60 males and 40 females for your analysis. So this technique is used when uh, we want each subgroup, to fairly represent the population, right? But if we use random sampling, we might take one, two, three, four elements from this and one element from this and none from this subgroup. So it's not fairly representing the population, right? So therefore we use stratified sampling. So based on a characteristic, we group them. Then using random sampling, we randomly pick elements from that subgroup, right? So this will ensure that sample fairly represent the population, right? Then we have systematic sampling. Systematic sampling. So systematic sampling means first we list the population, then we choose a random starting point. We select a random starting point and we pick every nth individual. We pick every nth individual uh, individual from that list, right? So example, let's say we have uh, 50,000, let's say 5,000 employees. So we start from the third person and pick every 50th employee, right? Every 50th employee. So we will get, let's say, like that, we are getting a 3, then 53, then 106. Likewise, we are getting a sample like that, right? So this technique is used when the population is ordered and you want a quick and evenly spaced sample. So, evenly spaced sample, right? So then we have the cluster sampling. The population is divided into clusters based on uh, let's say oftenly based on geography or the groups, and uh, here in stratified sampling we use random sampling to pick every element, pick an element from that uh, subset, right? So here the cluster sample, we divide the uh, population into clusters, only based on geography or groups, right? So then we uh, then the entire cluster is selected, right? In this case, these two clusters are our sample. So we are not considering about every cluster. We select clusters, entire cluster, uh, entire cluster randomly selected, right? So pick whole groups, not individuals, right? Pick whole groups, not individuals, right? So this technique is used when the population is widely spread and it's hard or expensive to sample individuals directly. So as an example, when we are uh, surveying about a country, so rather than taking a whole, rather than considering getting individuals from all over the country, we might select five or three or two, three or five cities and survey residents in those cities rather than the entire country likewise. So that's cluster sampling, where this technique is used when the population is widely spread and it's hard or expensive to sample individuals directly, right? Right. Then the sampling techniques or the sampling methods, can broadly categorize into two types. Broadly categorize into two types. Two types as probability sampling and non-probability sampling. So we discuss about simple random sampling, stratified sampling, systematic sampling, cluster sampling. All of these four was based on the probability sampling. They were probability sampling techniques. And we have non-probability sampling as well. So, uh, so what is probability? We discussed what is probability. 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 So probability is the measure of how likely an event is to happen. How likely is an event is to happen, right? So that's probability, right? Uh, right. In probability sampling, every member of the population has a known, or non-zero chance of being selected. Right? Every element in the population has some sort of probability getting selected. Let's say think in random sampling, we pick randomly elements from the population. So therefore, uh, therefore, every element had an equal chance of getting selected. So in stratified sampling, divide our population into subgroups, and we pick elements uh, from that subgroups, right? So they are also, every element in the population had the chance of getting selected. So in systematic sampling, we select a starting point and uh, select every nth element, right? So therefore, they are also based on the starting point, we select every element has a chance of getting selected, right? Then cluster sampling. So we divide our population into clusters. So every element is somehow belong to a cluster, and there is a probability of getting that cluster selected, right? So in probability sampling, every member of the population has a non-zero chance of getting selected, right? There is a non-zero chance of getting selected. Then we have the non-probability sampling. Non-probability sampling. Every member does not have a equal chance. Equal chance of getting selected, right? So that will introduce that, because of that, there can be bias results. So because of we are using non-probability sampling, there can be bias data in our sample. So the results may not represent the actual uh, population's uh, uh, characteristics, or the actual scenario, right? So so this will be using. So then why will be using this? So this will be using in uh, time limited limited studies. So we don't have the time to do collect a sample. So there we use non-probability sampling methods like convenience sampling, purposive sampling, voluntary response sampling, like that. So convenience sampling is uh, so sample whoever is easiest to research. So we pick a sample uh, who is easier to research, right? Researcher find a sample based on his convenience. So example, as when we want to do a research about the university exam preparation of students, rather than selecting uh, the uh, the sample from entire university, he will select some friends for his convenience. So that is convenient sampling. Then we have uh, judgmental sampling for the uh, purposive sampling. So the analyst will select who he thinks is the most useful. Who he think is the most useful. Then we have snowball sampling. So they are existing subjects recruit future subjects. In snowball sampling, existing subjects recruits future subjects. Existing subjects recruit future subjects. So this will be commonly using in hidden populations. Determining sample size is also important, right? So determining sampling size is important because uh, the determining right sample ensure your findings are uh, findings are uh, statistically valid, statistically valid, uh, and and accurate. Determining the right sample size ensure your findings are statistically valid and accurate. So the right sample size, determining right sample size will be based on effect size, statistical power, then significance level, and the type of test. Type of test. Type of test. So we will be using tests like t-test, ANOVA, regression. So based on that test, uh, the sample size will be different, right? Sample size will be different. We can use formulas like Slovin's formula to determine the sample size. N is the sample size, capital N is the population size, E is the margin for error. Margin for error. So it's like 5%, 5%, that means 0.05. So we can use a formula like Slovin's formula or the Cohen's table to determine the sample size. So determining sample size is important because it ensures that our findings are statistically valid and accurate, right? Okay. So we had the population. We need to take a sample which represent the population sufficiently. So we use sampling techniques. So sampling techniques are uh, can broadly divided into probability sampling and non-probability sampling techniques. Uh, Probability sampling works random, simple random, stratified, cluster, systematic. Likewise, then we had non-probability sampling like convenience sampling, historical sampling, purposive sampling, likewise, right? So then we need to determine the sample size. So which will ensure that our findings are statistically valid and accurate. So we can use techniques like Sloan's formula, Cohen's table to determine the sample size. After collecting the data, we have the data pre-processing. Pre-processing. So data pre-processing means we process it before analyzing it, right? So, data pre-processing helps in cleaning and organizing data in a structured manner. Data pre-processing helps in cleaning and organizing data in a structured manner, right? So, because why we need data pre-processing? Why we need data pre-processing? Because most of the time, real-world data sets are messy and unstructured. Messy and unstructured. So they will contain missing values, inconsistent data, noisy data, likewise. So the real data sets are messy and unstructured most of the times. So when we analyze that messy data, the accuracy of the analysis results are significantly lower. So therefore, before analyzing, we need to do the data pre-processing. So data pre-processing will uh, improve the accuracy of the results, reduce errors or bias in the models, and will remove the irrelevant data and improve the efficiency, right? And it will ensure the data quality. So data pre-processing will ensure, so the data pre-processing will ensure the data quality. Right? Data quality means how well a data set fit for the purpose. Right? How well data set fit for the purpose. So we measure the data quality using the accuracy of the data, completeness, consistency, timeliness, interpretability, and accessibility. The steps involved in data processing are data cleaning, then data integration, data reduction, data cleaning, data integration, data reduction, or data transformation. So the steps involved in data processing are data cleaning, data integration, data reduction, data transformation. So what do you mean by data cleaning? First, let's see what is data cleaning, right? So data cleaning. Data cleaning involves removing or correcting the missing or irrelevant data, incomplete or inconsistent data that can give biased results. So the following techniques can be used to clean a data set. So remove a noise data, filling missing values, removing duplicates, correcting inconsistent data. So noisy data means meaningless data. Meaningless data. So then missing data. Missing data means some data is missing in the data set. So there we can handle it in various ways, like our data set is large, we can ignore them. Otherwise, we can fill them with, let's say, average or the mean or the most probable value. We can fill them, right? For a data set is large, we can ignore them, or we can fill. If not, we can fill them using a probable value. Then we have the noisy data. Noisy data means meaningless data. So we can use techniques like clustering, regression to remove those noisy data, right? Right. That's data cleaning. So data cleaning will ensure that incomplete or inconsistent data will be removed. So therefore, we will not get biased results. Right? Then data integration. Data integration is the process of combining data from multiple sources. So combining data from multiple sources. Many data sets contain information from different sources. Right? Many data sets can uh, contain information from different sources, which can lead to missing or inconsistent data. Right? So data integration helps to resolve these issues and create a cohesive data set. So these following techniques can be used for integrating a data set. So merging data from different sources, resolving naming inconsistency, handling duplicate entries, and convert data types. Then we have data reduction. Data reduction means large data sets are often unwieldy and difficult to work with. Right? So therefore, we need to reduce it to a reduce it because it will simplify the data set. Large data sets are often unwidely and difficult to work with, right? So there can be irrelevant or redundant data. So because of that, we are minimizing it to a smaller size, or before that will give us a simplified data set. So following techniques can be used for reducing a data set: selecting a subset of the original data set, remove irrelevant features, aggregate data, and apply dimensionally reduction techniques such as principal component analysis, right? So then we have the data transformation. Data transformation involves the application of mathematical and statistical techniques to the data set to make it more useful and easier to work with. So it includes like scaling features like normalization uh, 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 and transform into linearized relationships. So we can use normalization, regression, those things to uh, transform the data. So these following techniques can be used for transforming a data set. Normalization, right? This will make our data set more useful and easier to work with. Right. So, okay, now we have the data set. We had a population. From that population, we get a sample. From that sample, we collect the data, and we had we have pre-processed that data. So we after the pre-processing, we get a structured data set. Structured data set. Now we can move to feature extraction. So feature extraction is the process of transforming raw data into a set of meaningful and informative uh, variables. We call that features. So that can be used for analysis. So imagine you have a data set of handwritten digits, right? Let's say images, and you have a data set of handwritten digits. So each image has a thousands of pixels, but not all of them are useful. So uh, the feature extraction will pick things like the number of blacks was white pixels, then uh, then so now instead of analyzing the pixels, you only work with a few important features that represent the image, right? Likewise, so feature extraction is uh, the the process of transforming raw data into a set of meaningful and informative variables. So then we have the clustering. Clustering is basically uh, grouping similar data points, data points, points together based on features. Clustering is grouping similar data points together based on uh, their features, right? So we do clustering to uh, discover patterns, discover patterns. We do clustering to discover patterns in the data. So as an example, so suppose you have a customer data set with features like age, spending habits, spending habits. Likewise, then based on that, you can cluster your customers like budget shoppers, budget shoppers, shoppers. Then premium customers, premium customers. So you can understand based on the features, based on the features of the data set, we are categorizing them, right? So then we can understand patterns in that data, right? So as an example, if you have a customer data set with attributes like age, spending habits like that, so you can cluster them as budget shoppers, occasional buyers, premium customers, likewise. So uh, right, so that's clustering. So now let's move to predictive analytics. So in descriptive analytics, we learn how we can summarize data, how we can summarize data. Here we're going to learn uh, what we can predict, what are the future outcomes. So we are going to predict future outcomes, right? So predictive analytics use data to determine the probable outcome of an event or likelihood of a situation occurring. So as discussed, we are using techniques like linear regression, time series, data mining to do the predictive analytics. So right, you can remember we discussed about random variables. Right? You can see, remember we discussed about random variable. A random variable is a numeric value that represents the outcome of a random process for an experiment. So we discussed that in Excel sheet, also uh, uh, we can have attributes like age, gender, uh, likewise. So each attribute we can consider it as a random variable, right? We can consider it as a random variable, right? So here what we are trying to do is identify the relationship between each variable, So as an example, uh, let's think, is the study hours will affect the exam score. If the exam study hour will it affect exam score? So here we are trying to find out the relationship between variables. So we call that Pearson's uh, correlation coefficient. So it's a statistical technique that quantifies the strength and direction of the linear relationship between two continuous variables. It, it is a statistical technique that quantifies the strength and direction of linear relationship between two continuous variables, right? It provides a value between -1 and 1, -1 and 1, where -1 indicate a negative relationship, perfect negative relationship, and 1 indicates perfect positive relationship. Negative relationship means if when x increases, y decreases. So positive relationship means when x increases, y increases, right? Then 0 means there is no linear relationship between two variables, right? So here we calculate how strong is the correlation, then in which direction correlation goes. So we analyze how strong the correlation is and which direction correlation goes. So the equation to find the correlation coefficient is R equals sigma xi. Xi means the individual value or the variable, let's say age, minus x bar, the mean of the variable, right? So mean, let's say xi is the age. We subtract the average age, then yi, individual value of, let's say, salary. So we are trying to analyze salary, age, and salary. What is the salary? What is the relationship? Will salary increase with the age, or will salary decrease with the age, or is there no relationship between these two variables? So equation is R is equal, Pearson's correlation coefficient is equals xi, I means data point minus x bar yi minus y bar divided by square root of sigma xi minus x bar square yi minus y bar square. So this is the equation to find the correlation coefficient of both values. So this will give us a value between -1 and 1. So -1 means perfectly negative relationship, and 1 means perfectly positive relationship, and 0 means there is no relationship between the variables. So here you need to think, right? Here you need to think. So basically, right, we derive the data from a sample, right? For the population, because we can't take the entire data from the population. We take a sample and we do analysis on the population. So let's say we calculate the correlation coefficient. So how can we ensure that the 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 the, the correlation coefficient calculated for the sample, uh, so is there a correlation in the population also? So how can we know is there a correlation in the population also? So to do that, we use hypothesis testing. To do that, we use hypothesis testing, right? Think as an example, uh, I want to collect data uh, of, I want to analyze whether is there a relationship between age and salary, age and salary. The age and salary they get paid. So so my population is the working class of of Sri Lanka. So I'm taking a sample, let's say 100 people. So here we only have a sample, not full population of Sri Lanka. So so we calculate the sample correlation coefficient R from that sample. So but we we want to know, is the sample result just due to chance? Is the sample results just due to chance, or is there a real correlation in the population? So we need to know, is that relationship exist in the population also? So to do that, we do a hypothesis testing. So to answer that, we do a hypothesis test for the correlation. So we start by assuming there is no correlation in the population. We assume that there is no correlation in the population. So that is our null hypothesis, right? Right? There is no correlation in the population. So our alternative hypothesis is there is some correlation in the population. It can be positive or negative. It can be positive or negative. So so this symbol represent the population correlation. So how we test this hypothesis? So we use sample correlation R and calculate test statistics. Then, so how we test this hypothesis, right? So then from the sample correlation, we calculate the test statistic. Then we find the p-value. So if the p-value is small, smaller than our level, if p-value is less than significant level, we reject the null hypothesis. Null hypothesis. So that means there is a correlation in the population. The p-value is less than the uh, 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 significant level, we reject the null hypothesis. So that means we accept the alternative hypothesis. So that's what we do. You understood, right? So we need to check whether there is a correlation between two variables or between the variables. So what we have is the sample. So we want to check whether this relationship exists in the population also. To do that, we have to do a hypothesis testing. So in hypothesis testing, first we define our hypothesis. So there is null hypothesis and the alternative hypothesis. So in this case, null hypothesis is we assume that there is no correlation in the population. So in the then the alternative hypothesis is there is a relationship between two variables, right? So then using using a statistical test, we calculate the p-value. Then value or the probability value, right? So then we check whether the probability value or the p-value is less than the significant level. If it is less than significant level, we reject the null hypothesis. That means we accept the alternative hypothesis. So that means there is a relationship between, there is a correlation in the population as well, right? P-value can be calculated using a statistical test, right? Like t-test, right? R, R, N, N, 2, and square root of 1 minus R square. 1 minus R square. So this, so this p-value need to be smaller than the specified significant level, which is usually let's say usually a 5%. So if this p-value is less, we can accept the alternative hypothesis, that is our data is our we can accept the uh, alternative hypothesis. That means there is a correlation in the population as well, right? So basically that's what we do, right? Okay. Then to calculate p-value like this, we need our data need to be normally distributed. Our data need to be normally distributed. So so let's discuss more about this probability distributions. So let's discuss more about this probability distribution. A probability distribution simply shows all the possible outcomes of an experiment and their probabilities, right? The probability distributions can be discrete and continuous. So discrete probability distributions are binomial, Poisson, and continuous probability distributions are normal, uniform, likewise. What do you mean by discrete one? So it's as an example, you can think about you are rolling a die. So you get values like 1, 2, 3, 4, 5, 6. So the values are discrete. So that will let's say uh, let's say you roll the die 10 times. So you will get 1, 2, 3, 4, 5, 6, one of that value 10 times, right? So the the distribution is discrete. That kind of a distribution we call discrete. So, but let's say you are measuring a height of a student. So that kind of data is continuous, right? Right? They are not like 1, 2, 3, 4. Likewise, that kind of distribution is uh, a continuous distribution. So first we will discuss about binomial distribution, right? Uh, so imagine you are tossing a coin 10 times. You are tossing a coin 10 times. You want to know what is the chance I get exactly 6 heads. Imagine you are tossing a coin 10 times and you want to know what is the chance I get exactly 10 heads. This is called a binomial experiment. This binomial distribution show the probability of getting 0 head, 1 head, 2 heads up to 10 heads. You see, so getting exactly 5 heads is the uh, most likely. So because there is only two possibilities, uh, like head or either tail. So if you turn it 10 times, most probably you will get 5 heads or 5 tails, right? So there are many possibilities, a possible combination to get 5 heads and 5 tails. So, and getting 0 10 times is low, right? Like if this is not 10, let's say, imagine you toss the coins 10,000 times. 10,000 times. So most probably it's 50-50, right? 5,000 times you will get uh, head, 5,000 times you will get tail, right? And getting 0 is very rare, right? It's very rare when getting 0 10,000 times. Or getting head 10,000 times is also very rare. Equals K number of heads, getting heads uh, is equals n K times P K times 1 minus P n minus K. So this will give us the probability of getting head in the kth time. Right? So this will give us the actual probability of getting uh, that, let's say, head in the particular point, right? So if we calculate actual probability, we will get values like this. Getting 0 is like 0.0.01 and getting 10 is extremely low, and most probably you will get 5 times you will get heads, right? And heads, number of heads, and the probability free. So getting 0 is my probability distribution will look like this. So I will get a distribution like this. So this is we call as binomial distribution. So binomial distribution we get with discrete data, right? So then we will discuss about this normal distribution, or we call this as the Gaussian distribution. So it's as an example, imagine you are measuring the height of 1,000 students. So you will see, and most of the students will be around like 160 to 170 like that. So, and there will be some students who are very short and some students there who are very tall. So, and there will be very extremely short students and extremely tall students in very rare cases. So if you uh, uh, draw a graph, so you will get a bell curve like this. If you draw a graph, you will get a bell curve like this. So most of the values cluster around the mean, and further you deviate from the mean, the fewer values you will see. So this we call as the Gaussian distribution. So this is important because many real world phenomena follow this normal distribution, right? So you can using this formula, you can ensure that particular value is following a normal distribution. So these are statistical concepts, right? So because why we need these? Why the thing is, right? The thing is why we need these things in data analytics. What you need to understand is that the thing is why we need to understand these, like this probability distribution. Is it a normal distribution? Is it so a normal distribution? So why do you need to have that understanding, the statistical understanding? Uh, because uh, uh, normal distribution, or because most of the statistical techniques, like as an example, we saw t-test, right? To do the t-test, you need to first ensure that the particular particular data is following a normal distribution. So that's why you need to have this understanding, right? So uh, uh, so this distribution is telling us what's typical and what's rare. So the typical value is this, what's typical and what is rare. That's what this distribution tells us. Then we have this something called empirical formula. Empirical formula denote that in the normal distribution, 68% of data falls within first standard deviation, then 95% of data falls within second standard deviation, mu minus 2 sigma, mu minus 2 sigma, then 99% of data falls within minus 3 sigma. So this we call as the empirical formula. So in a normal distribution, we have this empirical formula which ensures that 68% of data falls within first standard deviation from the mean, and 95% falls within second standard deviation from the mean, and 99% of data falls within third deviation from the mean, right? So that we call as empirical formula. So we need this understanding in data analytics because most of the statistical techniques expect to ensure that whether this uh, data is following a normal distribution. So before going to the data test, like we discussed details, so we need to first ensure that it is following the normal distribution, right? All right. That's why we need to do a normality test. So the normality test is to check whether the following your data is following a normal or a Gaussian distribution. So basically we are checking, is my data normal or not, right? We are checking, is my data is normal or not. So you can use tests like uh, chip provoke test, basically like in correlation coefficient, uh, like we did in correlation coefficient, we ensure that our data is, we do a hypothesis testing. We are assuming that our data is not normally distributed. Then we do the statistical analysis and get the p value and check whether. Okay, so that's it for today then. So I think I have covered all the statistical concepts and all these mathematical parts need to do needs in data analytics. So now we can jump to the programming and do that. Uh, let's now we can jump to the programming and check whether how we can apply this knowledge in a real world data analytics project. Okay, so that's it for today then. Thank you very much for joining. Have a nice day.